Sure. If it's time, we'll start.
Okay.
All right. Well, welcome everybody. First meeting of the year for Life members, the Consultants Network, and we also have the Computer and EMB chapter and Electron Devices chapter with us tonight. To talk about Life members first, we'd like to let everybody on the call know that we are open to suggestions from members for new topics and speakers. Just send it to Kai and we will give it good consideration. And especially for Life members, you can consider being a speaker yourself because you've got a lot of experience. And we old folks like to reminisce. Some just talking about how things used to be will interest us for a while. You know, of course, technology is a good topic, but so is finance or hobbies or travel and education. Your contribution to engineering, health and aging, and so forth. We also might take a tour or two through the year, which means actually getting out of the house or getting out of the restaurant and walking around a little bit. And this is the leadership group for Life members. I'm chairman. Tom Grimm is vice chair. He's on the call. I'm also treasurer. Clyde is secretary. He's on the call. Kai is the program manager. Thank Kai for all of the good topics that we cover throughout the year. John Purvis is our webmaster. He's on the call. And Dennis Ferguson is in charge of communications for us. I have not seen Dennis yet, but we're always looking for new volunteers, and I'll show you why in just a second, because I'm also going to speak for the Consultants Network. Louis Bosto is the chairperson. He is unable to join us, so the Consultants Network promotes development of members' careers, professional and social networking. We hope to get back in person sometime this year and start doing more of that networking thing. And we are here to publicize members' skills and present opportunities for consultants in the Central Texas area. Here are the officers for Consultants Network, and you'll notice many of the names are the same. And that's why we're looking for more volunteers. We can make adjustments throughout the year, but Louis is the chairman. Jody Everett is not on the call. He's vice chair and treasurer. You notice double slots in both of these groups. I'm secretary. Kai Wong is the program manager, and we have a very good, very opinionated member at large, Sergio Lieberman, who keeps us honest. And we're looking for a webmaster for the Consultants Network. Louis has to try to do that himself, and he will readily admit that many people have more skill. And then that brings us to tonight's meeting. So this is where I turn it back over to Kai. Can you see it, Kai?
Yes.
Okay.
Yeah, I'd like to introduce Mike. He's a senior fellow of AMD Advanced Micro Device, which is headquartered in San Jose, but actually really in all the active, most of the senior people are in Austin, Texas. And he's working in advanced memory technology and architecture. He has 27 years experience in IBM mainframe, and also working at Watson Research Center. He had about 25 patents and participated in many panels and major conferences. And in AMD, he served as principal investigator of the Department of Energy Fast Work and Fast Work 2 research program. He has also a program, and he successfully bring the frontier Exascale system beat. I know him many years ago from the World Society, Future Society, Society group, and he was a president at that time. And so please, next page, please.
Oh, I didn't.
Okay.
I didn't put any more in, Sky.
Okay, yeah. Okay. So I think the Exascale is a 10 to 18, a very high speed high performance computing product and using AMD chips. And as you know, AMD is one of the chip manufacturer who's first in competing with Intel. Now have its own architecture and exceed the performance of Intel in many ways. And I'd like to introduce Mike to you and talk about these exascale high performance computing topics. Mike, you have the mic, please.
Well, thanks, Kai. Let me do a screen share here. See if I can pull up some slides.
So it looks like sounds like the voice a little bit low. Maybe you can get closer to your mic or computer. Okay.
Okay, I'll turn it up a little bit and speak louder.
Oh, okay, yeah, it's better.
That's good. Okay. So as Kai said, I'm working now in AMD in Austin here as a senior fellow in the research group. I did a lot of work on the research that led up to the exascale systems, and I'll talk a little bit about that. First, let me say that given the size of the group, I welcome any quick questions or short comments, even open to some jokes, as long as they're about government or our competition or Elon Musk. I'll enjoy any of those.
Yes.
Let me start with a little bit of story about giving presentations. Many years ago, I went to my first computer conference, which was a ISCA conference in Seattle. And I still remember one of the first presenters of a research paper, young man from Intel, got up and said, "Well, I have good news and bad news today. The good news is our legal department said I can say anything I want about this research. The bad news is that kind of implies we decided not to use any of it in our roadmap products." And that was my introduction to the legal reviews of technical papers and public presentations. For many years, AMD, when we had a small market share, was reasonably lax about giving presentations and publishing papers. As long as you didn't say anything confidential or get AMD into legal trouble, they were fine. But last 4 years or so, AMD has been very successful. And the new policy is that our competition is paying very close attention to every word we publish and every presentation we give. So there's now a detailed review process that everyone has to go through, including me for this presentation. And it's the same in all companies now, really. But there were a couple of tricks that people in the industry developed. One is that they only review the contents of the slides. So if your slides have a lot of pictures and graphs and very few words, they go through the process easier. And then when you get into the meeting, you can actually talk quite a bit about each slide. And I'll be doing that today. The other is just stick to slides that have already been approved for other presentations. And I'll be doing some of that today. But I'll go above and beyond what the slides actually show. So let's go to the first slide with a bunch of pictures on it. This is actually from the Department of Energy on their high-end high-end supercomputers, basically, leading up to the Frontier system, which is the world's first official exascale system. It means it does an exaflop, or 10 to the 18th double precision floating point operations on the LINPACK benchmarks. The Department of Energy has a bunch of big laboratories around the country that kind of divided into two main thrusts. One is the Office of Science, which works on, everything from simulations of astrophysics to materials to energy efficiency to biological processes. The other is the NNSA, which is responsible for, among other things, our nuclear stockpile preservation. And what this means is that America and the other major partners or other major nuclear powers have not actually exploded any nuclear bombs, even test explosions, since about 1993 as part of the Comprehensive Test Ban Treaty. And the question is, how do we know any of these still work? I mean, they have a lot of very complex chemical materials in very close proximity to highly radioactive material. So they do some very detailed computer simulations of how these things age over time to determine what has to be replaced on what schedule and so on. And I know some of the people working on this, they work in the labs kind of below that horizontal dashed line. And to do this type of work, it helps to have a dark sense of humor. As one of them said, if I don't do my job properly, millions of people could live. So the actual series of supercomputers at the DOE labs are shown here. The Frontier system, as I mentioned, became this past summer the first system to actually break an exaflop. It's made from AMD components, CPUs and GPUs. It's actually the GPUs that do most of the calculations there. And then HPE is the system integrator. They provide the interconnect network to bring this all together. And they're responsible for actually delivering the system. And this one went into Oak Ridge National Labs in Oak Ridge, Tennessee. It's one of 3 exascale computers that the US is building. The second one, Aurora, below it, has kind of an interesting history. It was originally planned for a pre-exascale system, well below an exaflop, in 2018 with Intel components. It was based on an Intel architecture that was called Knight's Landing at the time. And sometime after signing the contract, Intel basically canceled that architecture. They said it was not going to be a commercial success. But instead of canceling the program, they were creative enough so that they renegotiated with Argonne National Lab where it was supposed to go. So instead of a pre-exascale system in 2018, they signed a contract to build the world's first exascale system with the new architecture in 2020. Well, that got delayed, and that got delayed 21, 22. But this year they have started apparently actually delivering some of the hardware to Argonne National Labs. So it will probably be going in and be brought up in this year, 2023. The Perlmutter system there is a pre-exascale system. I don't know why the DOE put it on this slide where it did. Same with the Crossroads system below that. The third real exascale system going in is the El Capitan system. And that also is made from AMD components, but the next generation after Frontier, along with HPE and their next generation switches, going in Lawrence Livermore National Lab, again, sometime near the end of this year. So when we have that, the US will have 3 exascale systems up and running. The interesting part is there are no Chinese systems on here. There have been rumors for a while that China has had not 1, but 2 exascale systems up and running for a while now. But for some reason, they never submitted official measurements to the organizing body here, which is the top500.org, to demonstrate that they actually did get an exascale measurement using LINPACK double precision floating point. So nobody really knows what's going on there or why, but there's a good chance that China also has 2 exascale systems up and running. Any questions on that? Okay. So that the top supercomputer in the world has performance growth rates of 2x every 1.2 years or so, roughly a factor of 1,000 in a decade, or a new decimal prefix every decade, which is actually faster than the Moore's law growth. And they accomplish that by just going to bigger and bigger systems using more and more power. Once they passed a petaflop about a decade ago, they realized getting to the next decimal prefix exaflop was actually going to be very hard to stay on this trend line. So the DOE started funding a lot of research programs. They were called Fast Forward and Fast Forward 2, Path Forward, Design Forward, and so on. And they gave out research money to all the big vendors here, IBM, Intel, NVIDIA, AMD, HPE, and Cray, and so on. AMD pulled in a fair amount of that research money. And it's actually helped fund my salary for the last several years now. And it paid off well because the research we did eventually helped AMD win a bid to get the Frontier and then the El Capitan Exascale systems. In some sense, the DOE had a goal of making sure there's a healthy ecosystem of component suppliers. So AMD and Intel and NVIDIA actually are all in the hunt for the next system after this, which is a good system. It's what the DOE wanted to accomplish. Unfortunately, on the system integrator side, HPE is becoming the sole company actually putting these things together and providing them. So they have kind of a monopoly there, and that's the DOE is concerned about that, but that's the way it worked out. So if you're wondering what's the next decimal prefix, which is 1,000 exaflops, it is a zettaflop computer or a Exascale computer. And if we were to stay on the trend line, that should come up in about 10 years. Well, the exaflop systems already fell off the trend line a little bit. They came out 2 years later than would the trend line would indicate. And so we expect the zettaflop system to come out even further behind schedule. But quite frankly, it's not looking good for even coming close to the schedule. We'll talk about the technology scaling problems in another slide or two. But boy, all the people involved in this saying, you know, we know how to get to 2 exaflops, maybe pushing the technology a little bit, we can get to 4, 8, 16, maybe even pushing it to 32 exaflops. But a zettaflop is 1,000 exaflops. We have no idea how to get there with the technology. So it's going to be a while before that happens, unless the government comes forward with a lot of new funding for the research programs. Now, the CHIPS Act that was passed this summer has some funding for that. It's mainly known as a way to increase the chip fabrication sites within the country. And it's should be do a good job at making that happen. But there's also funding in there for research and development over a wide range of topics. Some of it's computer related, some of it's science related. There's even funding in there for exobiology and astrobiology, which is a search for life on other planets, which I thought was really interesting. And then there's also funds in there for workforce development. They realized that if you do produce all the fabs in the US you want, plus all the supporting infrastructure to do the packaging and so on, plus the whole ecosystem of suppliers around that, it's going to take about a factor of 10 more people than we are currently graduating from the US into these areas. So they realize that's a big problem. They have to start working on workforce development. Now, as aggressive as this situation is, there's even a worse trend line. And this is the machine learning trend line. The largest machine learning models are growing at an astounding rate of doubling every 3.4 months, which is just making everyone's head spin. Chat GPT is the big one right now in the news. And there's no sign of the trend slowing down after that. And quite frankly, there's a lot more money to be made here than in selling supercomputers to the DOE. So a lot of companies are now investing their funds more into the machine learning area than into the high-end supercomputers. And the DOE recognizes this, and in fact, is beginning to believe that maybe the right goal is not to race towards a zettaflops of double precision impact performance, but start thinking about systems that combine brute force calculations with machine learning to guide it. And there's a lot of exploration going into that. They hold up as the classic example of protein folding. It turns out to be a really hard problem to calculate from first principles using just raw computing power. But machine learning systems have actually demonstrated some really good capabilities of coming up with reasonably accurate, reasonably good projections of protein folding calculations much, much quicker than you could do with the supercomputer approach. So that's an example of how machine learning and HPC supercomputers could be working on the same types of problem together in the future. And really the goal of the DOE is to do more science. It's not just to do bigger and bigger computers. So technology problems leading to all this. As many of you are probably aware, there's been a history of Moore's law scaling, really Dennard scaling, as devices shrink year after year after year. And as the components, the devices, the wires, and the transistors shrink, not only can you get more of them on a chip, but they become faster and more power efficient. So this is all goodness. Unfortunately, it's getting so hard to do that we've fallen off the historic trend line now and are moving further away from it. This shows 10 and 7 nanometer devices. AMD and a couple other companies are actually shipping 5 nanometer processors now. And TSMC and Samsung have both announced they are starting to produce chips at the 3 nanometer generation. No one is shipping those in products yet. Interestingly, the company most likely to ship this most advanced complex technology first will probably be Apple in their iPhones, simply because it's more power efficient. They get more bang for their buck there, and they have the volumes to justify it. That's a weird turn of events. There are problems with even staying on this trend line. And it has to do with the technology becoming so complex that the cost to produce a chip is rising dramatically. Now, you might think that, okay, the cost of the chip is getting bigger, but there's more components on it. So maybe the cost per transistor is still shrinking. And that was true for a number of years, but not anymore. The last couple of years, the cost per transistor has stabilized. And with 5 nanometer, the cost per transistor is actually increasing, which is not a good trend. People are still exploiting it because even though it doesn't get you more performance, it does get you better power efficiency. So the industry will still keep pushing for a while there, 5 nanometer down to 3 nanometer, and everyone's talking about how to get to 2 nanometer devices after that. What's not shown on the chart are two other problems. One is that the cost of building a fab and equipping it is almost doubling it each of these generations. And if you know about geometric doubling, you know the fabs are becoming pretty unaffordable pretty quickly. There's only a few places in the world that can actually afford to do this. TSE, Samsung, and Intel is trying to catch up, and they will eventually. And that's about it. The other problem is the cost of designing these. As they get more complex with more and more ground rules you have to follow, it becomes very expensive to design these advanced chips. The mask set, which is the set of masks that are used to actually etch the pattern onto the dies. A few years ago, it cost about $20 million to build a mask set for a specific processor chip. I don't know what it is now, but it's gone dramatically up since then. And at those prices, you can't afford to go through a couple of mask sets as you're trying to debug the chip and get it working right. So you have to spend an extreme amount of time and effort into verification to try and make your very first mask set work right. And right now, the verification is the longest component in the design cycle of the modern chips. So what else can be done here? This is a chart, a little diagram that I put together a couple of years ago, and it's been actually getting a lot of use around the industry. It keeps showing up at different conferences in different people's presentations. And what it's meant to show is that accelerators optimizing for performance and performance efficiency is an architecture way to keep things improving, even if the technology's improvements are slowing down. And what it's kind of trying to illustrate is that general purpose processors, x86 processors, for example, can be applied to a large set of applications, big application space. They're not really exceptional in terms of your performance or performance per watt, but they have a broad set of applications you can apply them to. GPUs are a form of accelerators. GPU is a general purpose GPU designed for more general purpose things than just literally a graphics accelerator. They do actually very well for applications that are highly parallelized and don't have too much branching. And they can get much better performance and performance per watt than general purpose cores. That's why they're used a lot in the large supercomputers now. But for applications that aren't parallelized well, or that have a lot of complex conditional branches, GPUs just don't work that well. And they actually can be outperformed by general purpose cores easily. And then if you want to go a step further, you can design specialized accelerator logic to really target a certain class of workloads. And they do really well for those workloads, but they really fall off on performance on anything they're not designed for. So there's only a limited market for these things, but it turns out the growing market where they are being used is in machine learning. And a lot of companies are now designing special purposed accelerators for machine learning because there's such a huge market there and can get such a big speed up. Another important development is the CXL bus standard. And let me explain a little bit about that. I think many of you will be familiar with the PCIe standard. It's a standard bus that connects processors to all sorts of different cards in a computer. And it's gone through multiple generations, but there's still problems with the protocol. It's less than ideal. So what the industry did is to design a new interconnect standard called CXL, which literally is built on top of PCIe. It uses the same physical interconnect, same wires and physical protocol. But it adds some changes to the protocol and adds some new commands. So it lets you do more accelerators and lets you talk about cache coherency between the CXL cards and the processor cards and so on. So what you can do now is build CXL memory cards that a processor can access as if it was just locally attached memory. And it can be cache coherent, and it just takes a little bit longer in latency, but now you can greatly expand the processor's memory space. You can do now pools of memory cards that can be shared by multiple processors. They can literally share the memory, or it can be allocated to each processor as it's needed. I apologize for all the noise in the background. My wife is just getting home. Hope it's not coming through too much. The companies that are building these memory cards are realizing that you can put a processor out on those memory cards really cheaply and build essentially an intelligent CXL memory card that can do database operations and a bunch of other things there. So I'm not announcing any confidential data to say that a number of companies are working on this. You can push flash memory chips out there. So you essentially have a CXL SSD card. And again, you can make that a computational storage card with some processors out there. And then just large address spaces of non-volatile memory. AMD just this fall came out with an announcement of our latest processors. I think they're the first ones in the market to support the CXL interface. I think AMD's FPGAs are also supporting it now. And as you go through this in the coming years, you get more CPU vendors supporting it, more accelerator and memory card vendors supporting this. CXL is going to be responsible for a flourishing of a lot of new innovation in the computer industry, simply because it allows you to attach a wide variety of things to each other. So that's a really promising sign in the future. Another big trend is integration of a lot of chiplets into the same package, and in particular, heterogeneous integration. You can put CPUs and FPGAs and caches and memory and custom accelerators, whatever you want. A lot of work's being done on this to explore how to do this. New packaging technologies to improve the bandwidth within the package. And just, it seems like there's endless configurations that people can put together. We're also doing that at AMD. And in fact, we have a long history of doing this at AMD. Many years ago, we and everyone in the industry would build their processors with just a big monolithic die in the package. In 2015, we were the first to start integrating a compute component. It was actually a GPU with HBM memory stacks. If you're not familiar with HBM, that is, think of it as up to 8 DRAM chips stacked on top of each other. And this actually shows 4 HBM memory stacks packaged together with a big GPU chip. Our latest GPUs that are used in the Frontier system actually have 8 DRAM stacks in the package with the compute chips. So we're really pushing that hard. That's sometimes referred to 2.5D integration. There's some 3D stuff in there and some 2D stuff in there. In 2017, we came out with our first chiplet-based processing chip, the Zen series of CPUs. It had 4 chips there. When you get to the really advanced lithography nodes, trying to use them as soon as possible is challenging to make a really big chip because the yield is low for big chips. But if you can build your system with multiple small chiplets hooked together, you get much better yield early in this life cycle of the new technology. So we started doing that. And now our latest chiplets are designed like the 2019 version there. And let me explain what's going on there. There are 8 little chiplets there. Those are actually the core dies. They have the processing chips, processing cores. There's 8 cores on each of those little chiplets. And then the big thing in the middle is called the I/O die. That has all the interfaces to the memory and to the PCIe and CXL and the interconnect between the processor chiplets and a bunch of other stuff there for maintenance and testing and power management and so on. And that big center die, that can be actually in an N-1 technology because you're not doing many compute functions there. You can actually make it a little bit cheaper by using a back level technology. And this is being used now in all our systems, and Intel and NVIDIA and all sorts of other companies have picked up on this and are building chiplet versions of their largest system. And then finally on the right, everyone actually is looking at even more advanced integration with more 3D stacking and other things. Excuse me a minute while I want to close the door. I'll be right back. Okay. As an example of 3D stacking, let me talk about the 3D V-cache that AMD is producing and selling now. Those little chiplets that where the processing cores reside, they actually look a little bit inside like this. The cores themselves are on the outside edges of the chip, and the middle of the chip is a big shared 3D SRAM cache. This is called our base CCD design. It's 4 complex die. So the initial they stand for. And if you think about that big SRAM covering the middle of the chip, you can actually take another SRAM chip and stack it up on top of that, which is kind of illustrated here. So the thing in the center is actually very thick because there's a SRAM on the bottom and another SRAM chip stacked on top of that. The 2 kind of white grayish things floating above the configuration there, that's actually just pieces of dummy silicon that you put down over the cores so that the top surface is nice and smooth and level and makes a better contact with the heatsink that you attach this to. It turns out when you get these really big 3D SRAM caches for L3, we're finding, or actually customers are finding, that a number of key workloads are starting to fit mainly within that L3 cache, or at least the main bulk of the working set. So they're getting much more performance improvement than we ever projected out of this, and they're very popular. We can see this as a way to go. Right now, we're just stacking 1 SRAM chip on top of the base die, but in the future, you can conceive of stacking more than 1 to get even a bigger L3 cache there. So that's a version of 3D stacking that we've already started in our shipping, and you can expect other things to come as we and everyone else in the industry is looking at this type of stuff. So let's talk a little bit more about this chiplet approach here. And as everyone in the industry starts adopting it, it results in a lot of interesting questions. Not only once you do this, can you configure a lot of different systems together with a base set of chiplets, but lots of interesting design questions come up. How do you interconnect the chiplets together? Everyone right now is using a proprietary fabric. For AMD, it's our Affinity fabric, but there's work underway to kind of do an industry standard protocol called UCIe for the chiplet to chiplet interconnect. There's questions about, given all these chiplets together in a package, how do you do power management for the package and debugging and security and all this stuff that everyone is working through slowly to make this a industry common thing that you can actually hook third-party chips up to. Memory models turn out to be one of the big issues here. How do these chiplets, often various types of accelerators, interface with the main central processor chip and the memory management? How do you make everything cache coherent here? These accelerator chiplets, usually, ideally, they work with virtual memory addresses. So they have to deal with memory translation. And what happens if an accelerator tries to access a memory page and it takes a page fault? You have to be able to handle that properly. So getting things to all work at the same memory model and virtual memory model is part of the big challenge. The other challenge is security. Because you can assemble things in so many different ways, trying to figure out if they're all are secure configurations gets to be quite a challenge, especially when you can start thinking about eventually hooking chiplets built by third parties into the system. How do you manage, make sure that that can introduce some security flaw? I'll tell you, a lot of architects fantasize or have dreams about one of those chiplets being an FPGA chiplet that you can attach into the rest of the processor complex there. Our security experts refer to that dream as more of a nightmare. And they say, if your vision is to let any user configure any type of logic you want in that FPGA, let me explain to you the many reasons why that's a very bad idea. So a lot of research work is being done on how to manage this and how to restrict what can be done with that FPGA and still guarantee that it doesn't run amok and violate all the security protocols and access memory that it's not supposed to be accessing and so on. So obviously, AMD is putting a lot of work into this. If you're not aware, AMD acquired Xilinx about a year ago. Xilinx was the largest FPGA manufacturer, which now makes AMD the largest FPGA manufacturer in the world, or at least the most advanced ones. So there's a lot of work on trying to integrate that into our systems. So this is an interesting summary slide talking about how the chiplets are the future. Right now, we're doing this 2D or 2.5D integration. More and more companies in the industry are looking at extending this to 3D integration to put more and more compute capabilities within a processor package, and how to standardize this and enable FPGAs and other third parties. Now, one of the other interesting developments that I did not make a slide for, because that would be a new slide and have a lot of additional problems trying to get that through the legal review, but I'll talk about it here anyway. Imagine the bottleneck in the system as you put more and more processing capability in a package. To get any data in and out of that package, you still got to go through all the pins on the bottom. And unfortunately, mechanical pins are not experiencing anything like a Moore's law improvement rate. You can improve the speed of some of those pins, but at a cost of getting more expensive in terms of the technology and the power consumed and so on. So that's becoming a major bottleneck. But if you look at that top picture and say, I'm going to remove one of those little chiplets and put in a photonics chip, a chip that converts electric signals to optic fibers and bring optic fibers out of the side of the package, that opens up the possibility of significantly increasing the bandwidth coming out of here. And a lot of people are looking at this now. A lot of startup companies are working on, it's called silicon photonics there. You're seeing more and more of this discussed at conferences. And it's kind of a race to get both the cost down, the power down, and the bandwidth up of those photonic chiplets within the package. And we may have another generation or two before we reach the end of the electrical interconnect speed. But after that, we're going to start seeing photonic interconnect packaged in with the processor chips, becoming more and more common in industry. And right now, there's a huge bandwidth within the package, and then a dramatic step function in the bandwidth as you leave the package. Well, the photonic interconnect will bring us to a space where that step function starts to disappear, and you can get almost as much bandwidth off the package as you have within the package. And that opens up a whole new world for architects to explore, because now you can conceive of a very large collection of packages that are optically connected and form some sort of large virtual, what looks like a single processor package to the software. And it's actually the machine learning world that's driving this, because they're pushing for the most dramatic growth in the processing and interconnect power that's available. So that's generating a lot of interest and causing a lot of money to be invested in research into photonic interconnect. And clearly by the end of this decade, which probably unfortunately is going to be beyond my retirement date, but you're going to see a lot of very high bandwidth photonic interconnect between packages, causing a lot of revolutions in architecture design. So with that, I will end there and open it up for questions or comments. Again, questions, comments are good. Prolonged debate is not preferred, but I know engineers have this habit, reputation for getting into longer debates.
Please open up your mic. I sort of unmute some of you because I hear some noise.
Okay. And I haven't been able to follow the chat window, so if anyone's posting there.
Hey, Mike, what is CCD that you mentioned that earlier?
Yeah, that's our internal name for the core compute die.
Okay.
So that's the chiplet that holds the actual x86 cores in the L3 cache.
Okay, all right, thank you.
Surprising that one got through the reviewers. They usually don't like when we use jargon like that.
Yes.
Yeah.
Yes, please unmute yourself and ask any question to Mike. So what is Intel doing in this area?
So they're doing something similar in terms of chiplets. The ones they're producing for their Aurora supercomputer. Boy, I wish I would have added a picture here, but they're taking some of this to the extreme. They have something on the order of 20, 30 or more individual chiplets in a package when you include all the memory chiplets. They're pushing the technology probably beyond what's cost effective at the moment, but these supercomputers have a tendency to push the leading edge technology, and Intel is certainly using that to push their leading edge technology in chiplets.
So I know a family friend's kid is working for TSMC, working on a 3D packaging. So do you have any special requirement for the fab side to enable this type of technology?
It only makes sense to build a fab for that if they can process huge volumes, because the fabs are getting so expensive.
Yes.
And people look at this complex 3D packaging and other complex things we're doing in the packaging area in photonics and saying, boy, that looks complex. Isn't that risky? And they have no idea of the risk associated with going from 7 nanometer to 5 nanometer to 3 nanometer. These are extremely complex, extremely risky technology transitions, far beyond anything we're doing in packaging. And in fact, that's kind of the source of a lot of Intel's problems. The technology they're pursuing was so risky that Intel's efforts failed at first, getting down to about 7 nanometer. Mm-hmm. And they had a long delay in that. So they fell behind TSMC, basically, which has caused a lot of their loss of market share. And AMD and NVIDIA both rely on TSMC, and we were able to exploit that. But so, yeah, I should have mentioned that in the slides. Not only is each new technology transition becoming much more expensive than the last one, it's much more risky than the last one, with all sorts of opportunities for delays and individual companies to experience major problems in the transition.
I see. I saw a comment from Donald. Can you speak out, Donald?
Yeah, I was wondering if Mike had any comments on the proposals for a 16-bit floating point, if that's going to improve his impact numbers.
Yeah, so the big scientific computations all stick around with 32, or it's double precision, which is 64-bit floating point, for historical reasons, among others. But machine learning can work with much smaller precision. So they're going down 32, 16-bit floating point. Believe it or not, there's even proposals for 8-bit floating point for machine learning, which is kind of surprising to me. Once you get to that point, why not just do 8-bit integers? But a lot of research is going into this. And if you have 8-bit floating point, you can do 8 of those operations with the same chip area that you do a 64-bit floating point. So that dramatically increases the compute capability of those new number formats. In fact, there are machine learning systems now that claim to be exascale systems, but they're only exascale if you count right now 16-bit floating point and or 8-bit integer operations. They can't actually do an exaflop of 64-bit floating points.
Where do the proposals for standardization land with the short precision, the very short precision floating point?
It's somewhat of a mess right now. Because every company is making their own proposals, and even Microsoft is getting involved in this because they have a really big machine learning effort, and they want other companies to produce. Right now, they have multiple proposals for 8-bit floating point formats, as does Google, as does NVIDIA, and I'm not sure what we're doing yet. We're just trying to figure out which one we want to support in terms of standardization. I have no idea how this is going to play out in the end. There's also proposals for a block of multiple floating point numbers to share the same exponent to further reduce cost and make things more compact, which works in a lot of machine learning applications, but not necessarily anything else. And I just don't know how it's going to shake out. It's a mess.
I've got a question about the changing the floating point numbers. It looks to me like that's going to cause real trouble when somebody tries to replicate a project. Having to, looks like the hardware dependency is going to be real big. So
yeah,
the guys writing the journal articles are going to have some trouble.
Right, they're going to have to talk about what specific floating point formats they used. There's even proposals for what they're calling logarithmic based or floating point numbers, where the interpretation of the exponent changes and it's not just a simple power of 2.
And I'm surprised it's staying with the x86 instruction set.
Yeah, it turns out to a large extent, the instruction set is less important than the technology and the software tools you have to support it. You can do a lot of really good implementations of x86. And now there's new architecture extensions called VMX, where they have long registers. You can kind of do a SIMD type of operations with x86. We are seeing more competition from ARM cores and RISC-V cores coming into play. Right now, there's just not the money going into implementing them and tools to support them that you see in the x86 world. But in the long run, they may become very important too. And of course, they're eventually going to have to compete with all sorts of other accelerator designs that are really optimized for certain workloads.
Investment is the answer to that. Yeah. The money's
Yep.
not flowing, so you stay where you are.
Yep. Especially with the software support.
Yeah.
It's the old joke, if you have the best processor in the world, but you can't run software on it, it's nothing but a complex sand architecture.
Yes.
I use that joke for some family members at times. They ask me what I do. I say, I help design tiny, tiny little sand sculptures. I get a strange look and they have to explain it. But you guys know what I'm talking about.
Yes. So I heard that Micron is introducing some 1-bit DRAM for the mobile device. Would Micron help your case in a large-scale computing? The advancement in Micron memory device.
Micron is reasonably successful in memory, trying to expand that beyond. I don't know the details of what they're doing. So stay tuned for some interesting announcements coming throughout this year, from the Aurora supercomputer to the El Capitan supercomputer to seeing what the Chinese announce if and when they make an announcement. And then there's European consortiums will probably announce supercomputer exaflop efforts, if not final completion. And I know Japan's looking at a multi-exaflop program too. So
Will these include exaflop operations for AI?
yes. In fact, AI, because it uses the reduced precision, can actually get well above an exaflop. And it's the same systems now that support 64-bit floating point will all in the very near future support all these reduced precision stuff too. So yeah, they can do it.
There's a question in the chat saying, are there any European companies or countries in this space?
There's some large European consortiums trying to get together to do a European exascale computer. A lot of it is based around RISC-V architecture, because they can do that in European countries and come out with some of the best RISC-V architecture chips in the world. So they're going that route, which means they have to invest money in the software tools and everything to support that. But yeah, they have consortiums of multiple countries coming together to try and build a European exascale computer. I can't remember the name of it at the moment, but it's happening.
Yeah, I think there's some of the big tech company in China doing the same thing using RISC-V. I think
Yeah.
Alibaba or Baidu or some of those guys
Mhm.
for the AI effort.
The top 500 supercomputers, which is kind of the list in the organization that specifies what are the official top ranking 500 supercomputers in the world, but most people only pay attention to the top 5 or so. We're waiting. They update the list once in the spring and once in the fall. Fall one is at supercomputing conference. So we're waiting to see what happens, every 6 months in terms of new entries being added to that list. We'll see if China gets in there this year, or we'll see if the Aurora and El Capitan systems get up and running and tuned in time to make one of those announcements too. The DOE still has, they claim they have problems where they want, if they could afford it, a zettaflop computer. Really big scale problems they want to do. But it's just not going to be there for a while. So there's the need, just not the ability to solve it.
Mike, are there any core microarchitecture changes in the base machines that you can talk about that are on the forefront to make some of these things work?
Hey, Bob. Yeah, so x86 architecture does the VMX instructions, which are long 256 512-bit registers that can do in parallel, like a vector operation. So Intel and AMD are both supporting that. And then a lot of the innovations are not in the x86 or related cores, they're in the GPU type of cores, where AMD and Intel and NVIDIA are all working on an advanced architecture there, and they all have a lot more freedom because the whole ecosystem is not built on a standard ISA there. It's built on higher level software abstracts, so they can muck around with the low level stuff a lot more and get away with it. So yeah, each new generation comes out with new features and ISA capabilities. And as I kind of alluded to, there's a lot of startup companies also working on machine learning accelerators, really optimized to do those very fast. And AMD has announced machine learning accelerators too, that we're ready to start marketing. So that's happening too. But these are all very low precision, 16-bit floating point and integer stuff, optimized for very fast execution of those types of things.
I can imagine what the problem set is that the government labs are working on. You talked a little bit about it in the start, but and I remember in the 60s and early 70s, the application that everybody was trying to do was FFTs. The Data 100 was the first of the hardware FFT boxes, and its prototype was roughly a cubic meter of ECL logic, and it had about a 20-minute time to run, and by that time the fans had vibrated the chips and they were coming out of the part. So but we had one on a submarine, so it was fun. And so I guess I'm having to imagine what the problems are that these guys are working on.
The Frontier computer, I sat down and did the calculation once. It has over 1 million DRAM chips in it. And we kind of told the memory companies, you need to step up your reliability here. Otherwise, that system would have a mean time between failure of just a few minutes before one of the DRAM chips somewhere in the system went down. So in the meantime, they have to do a lot of checkpointing and everything to accommodate that. The actual applications they use, so the DOE does a lot of basic science. As I said, there's lots of everything from astrophysics, calculations of the evolution of galaxies. They do a lot of work on advanced materials for increased strength. A lot of work, not too surprisingly, on what happens with explosive impact on a very advanced materials and how to make materials
Finite element
withstand.
kind of things, where you're
Yep,
busy
that's all
running
finite element.
a bunch of differential equations and finite element
Yep.
stuff. Yeah, okay.
A lot of the biological stuff it can't really be finite element. It's much more complex, and there's even Monte Carlo type applications for certain cases when you're looking at elementary particles and neutrons and protons flying through material, and you want to figure out what type of damage they do. You just do Monte Carlo simulations of millions and millions of particles flying through and just random at what molecules they hit and disrupt. And of course, the DOE is getting more into machine learning also.
This has been a good time tonight. Thanks.
Sure. Hey, Kai, can I put one more plug in for a different group before we leave? So last time Kai and I met was at the Austin Forum for Technology and Science,
Yes.
which is a really wonderful group. If you're in the Austin area, you can join them live. Great topics each month. If you're not in the Austin area, they actually do all their presentations online now too, this hybrid model. And just look up Austin Forum on the web, do a search on that to give you their website. And I suspect it's the type of thing this group would really be interested in.
Mhm. Yes. Yeah, I also want to announce that we did not do before. In the next 2 months, in February, we're going to do a Zoom meeting on 2023 investment outlook and investment market. And in March, we're going to have a local company, Sci-Fi, talk about RISC-V architectures and some of the applications. So it's kind of follow on what Mike is doing, but a different architecture. So any more questions from this group? And
Since we're taking the risk for shameless plugs, Kai, I mean,
so go ahead.
the Technology Advisors Group is meeting this a week from Friday. Last Friday of the month, we're having Worley talk about his work in their former computers. Just tag http://tagaustin.org. It's online 8 to 9 on the last Friday of the month. A week from tomorrow.
Yes, it's a topics quantum computing.
Quantum computing, yeah.
But on the software side, not hardware.
No, a little bit of each, a little bit of everything.
Okay, yeah.
Really does. He talks. I mean, he talks it all.
Yeah, right. Great. Yeah. Normally we ask our audience to say what they trying to present this month, next month. So thank you for that. So well, if there's no more question, I would like to call this a night, and thank you, Mike, for such a great talk about computing. So we're looking forward to see you guys February 16 or March 16 on different topics. All right. So Mike, can you send us the slide deck of yours? We'd like to publish in our website.
Yep, it's been approved. I can do that now
Okay.
without getting fired.
Great. Okay. Yeah. I think we've been exchanging. I used to work for Motorola. We exchanged engineer with AMD before. So some of our friends that work for AMD for a few years and come back and kind of back and forth.
Kai, thank you much for arranging a most interesting talk.
Yes, thank you.
Thanks to Kai and to Mike. Thank you guys. It was a great evening. Thank you.
Yeah.
Thanks, Bob.
Okay. Thank you. Bye-bye.
Bye.
All right. So